kids, Miss Kulkarni here. In this video, we will continue to discuss some of the analytical techniques, and we are going to talk about infrared or IR spectrum in this video. So let's begin. Let's talk about some principles on which IR absorption depends. The things to keep in mind that the IR radiation is of too low an energy to excite any electronic transition which we have. So it is a weak spectrum. Also, the main reason we get IR spectrum is because of the bond getting stretched or bending. Imagine a bond like a spring, and we can stretch the spring or we can bend the spring, and that's what happens in obtaining the IR spectrum. Also, there are some other movements related to that, and it is absorption related to vibrational and also the rotational levels of that bond. Now, for liquids and solids, we get the rotation is limited, so we get mostly vibrational energy there. And the last thing to keep in mind is different type of bond, single bond, double bond, or a bond which is linked to carbon and oxygen. They all will absorb at different energies and different frequencies. That's why they will correspond with a different stretch. Now this is a sample of IR spectrum. When you simply look at that, you just feel as if this is noise, somebody just scratching with pencil. But no, this is an IR spectrum, and what is marked here, those downward negative peaks, or they are called as stretches, those are the ones which are going to give us some important information. Like for here, I have marked this as A, B, and C. Those particular stretches tell me which groups I do have in the given molecule. How do we find out? Let's talk more about that. So these are examples of the compounds which contain a carbonyl group. There is carboxylic acid where we have RCOOH as the group. So we need to get two different peaks or stretches. We need to have a carbonyl, and we also need to have COH peaks. And where do they appear? That's the range where we should see the stretches. Let's move on to amide. Again, amide should be showing you a carbonyl peak, and then it also should be showing you a peak corresponding to NH2 or NH. Then there's an ester group. Ester is R1COOR2, where R1 and R2 are alkyl groups. So what do we need? We need to make sure we have a carbonyl stretch which will appear at 1820 to 1660, and we also need to make a single bond CO stretch also between 1300 and 1000. Then for ketone, ketone only will have a carbonyl group, but whatever we saw before, no hydroxide, no NH2, or no single bonded CO, and that indicates we have a ketone in that particular structure. Now what about some different type of molecules? If we have hydrogen in the compound, that will give a stretch between 3700 to 2700. What if we have a triple bond and double bond? Again, there is a range provided for those. So we can easily decide if the compound is an alkane or alkene, or is it going to be an alkyne. There is also something important to remember. This is called fingerprint region, and which is specific to a particular molecule. This is mainly for the single bond, and it appears between 1500 and 700. Now here is a table which is summarizing all the stretches and where they could be found, and either they are strong or they are weak or they are moderate. None of these things need to be memorized because you will be having a data table which will provide these values, and these are approximate ranges. So some of the textbooks may give you slightly different range, but as long as you get that stretch within that range, you're good to go, and you can say you have that particular peak. Like for example, we have OH cited here between 2500 and 3100. So you may get a peak at 2600, you may get a peak at 3000, and it will be still classified as an hydroxyl group there. Now let's go back to the IR spectrum which we saw initially. So in this compound, if you look carefully, we have a carbonyl stretch, and then we also have an aromatic ring. So look at the spectrum here, and we got these peaks or stretches as A, B, and C. Let's focus on A. A is exactly at 1730, which is within the range for a carbonyl group. That means this compound must have a carbonyl group. Then let's move on to the next part, B. B, this peak is at 1590, and this goes very well with an aromatic ring having carbon-carbon double bond. And the third one is CH aromatic. There is a single bond also between these aromatic ring carbons and hydrogen, and that goes at 3050. So kind of we can match the structure with IR, and we can conclude that yes, that probably looks like a correct structure. All right, what we got here, this compound looks like an alkane. Everything is single bonded and it's only containing carbon and hydrogen there. So what do we need to look for? We need to look for simple CH stretch, and of course there is sometimes CH bend. There it is, that's a CH stretch which is coming well within the range which is provided for any alkane range. Now unfortunately this does not give me any information about how many carbons I got or whether there is methyl group branch alkane there. It does not give me much information whether the alkane is a branched one or a cyclic one. But at least we know it's a single bonded alkane with CH stretch. This is another example of alkane, and still it does not give you much more information except showing CH stretch and CH bend. This is interesting. This compound now got an hydroxide group here, alcohol group here. So that alcohol OH needs to be quite downfilled here, which is right here we are able to see in the range of 3400 to 2400. And of course it does have CH bend also. So that concludes that we have an alcohol. Somewhere we have at least one OH group in the compound. Now moving on to the next compound. This compound has CCl stretch, and that CCl stretch will appear around between 790 and 870, and of course it does have a CH stretch for an alkane. So that means it's an alkane which has a chlorine group along with that. This one looks pretty interesting. Okay, it looks like as if this is the noise, and that's why we call this is the fingerprint region which we have. Now how can we identify the structure based upon the IR? There is that carboxylic acid group, and for that group we need to look for C double bond O carbonyl and also for OH group. Look over here, around 3000 what we stated was COOH stretch. Typically an carboxylic acid is the one which will show you kind of a little bit broader peak. It also has CO for ester group, and then that comes around over here at 1757. It also shows the aromatic ring. It also shows CH stretch. So your goal should be, when you look at the compound and IR spectrum, find out the functional groups and see if the spectrum has those particular stretches. If it has, that means you got the right compound. If you don't, that means your compound does not have that structure. It is that simple. So IR spectrum gives us very important information. It talks to us about the functional groups, if they're present or not, but does not give us any more details about how many groups or where they are located and how big or small is the compound, how many carbon atom links are there, and all that stuff. So it is useful, but not that quite useful analytical technique. So I hope you guys enjoyed the video. I will see you again in next video. Until then, bye bye.